In this sixth module, we are discussing weak interactions. In this second video, we introduce the operations of charge conjugation, parity, and time reversal. After following this video, you will know discrete transformation of space-time, which are parity and time reversal, the charge conjugation transformation, which reverses all charges, and the behavior of forces and matter under these transformations. The reversals of space and time directions are discrete transformation of space-time coordinates. For the space coordinates, the transformation is also called parity, P. Both transformations can be applied as operators to a quantum state, such as a particle. These operators are unitary, because a double application to the initial states reproduces the original state. Therefore, the eigenvalues of the two operators are plus or minus 1 if they are applied to eigenstates of parity or time reversal. However, there are many wave functions which are not eigenstates of parity. For example, a function phi equal to cosinus x plus sinus x becomes, under the application of parity, cosinus x minus sinus x, which is neither plus phi nor minus phi. Eigenstates of P can be classified like in this table. Scalar wave functions describe spin-zero particles with positive parity. Pseudoscalar ones describe spin-zero particles with parity minus. Vector and axial vector wave function describes spin-1 particles with parity negative and positive respectively. Parity is a multiplicative quantum number, so the total parity of a system in its ground state is the product of the individual parities of its components. If there is an angular momentum between the components characterized by an L-type quantum number, it must be taken into account by a factor -1 at the L power. Parity is conserved in reaction due to electromagnetic and strong forces, but not in weak interactions. Conservation means that if a system is in an eigenstate before the reaction, it will be in an eigenstate with the same eigenvalue after the reaction. For bound states, the total angular momentum J equal to L plus S comes in, multiplying the intrinsic parity of the components. Consequently, the notation Jp is used to characterize particles. You find it in the PDG tables for each particle. Electromagnetic transitions in bound states, as the hydrogen atom, for example, require delta L equal to plus or minus 1, so the parity of the photon must be -1. The photon is thus indeed a vector particle, as we noted in Module 4. Hadrons are parity eigenstates, thus their parity eigenvalues can be used to characterize a particle, just like a spin, electric charge, or baryon number. The parity of fermions is opposite to that of antifermions. By convention, parity is arbitrarily fixed to +1 for leptons and quarks, and antiquarks and antileptons therefore have parity -1. For bosons, the parity is the same for particles and antiparticles. The photon parity, as we already said, is -1. Baryons, which contains 3 quarks without a relative quantum angular momentum, such as proton and neutron, have a parity +1 at the third power. So, finally, parity +1. That is to say that Jp is 1/2 plus. The lightest mesons, like pions as well as light kaons, contain quark and antiquark with antiparallel spins. They have parity +1 times -1, so -1, and are called pseudoscalar mesons. The states with the same quark contents but parallel spins, like the mesons ρ, K star, omega, and phi, are called vector mesons. They have Jp equal to 1 minus. But parity is not just a theoretical concept, it has a measurable effects whenever it corresponds to a conserved observable. Let us look at the dominant decay of the pi 0, which goes in 2 photons. The study of this process has allowed to conclude that the pi 0 is a pseudoscalar boson with Jp equals to 0 minus. Its decay products are 2 photons, vector boson of Jp 1 minus. We project spins on the only natural axis of the system given by the direction of the 2 photons in the rest frame of the pi 0. Conservation of angular momentum requires one of the 2 configurations sketched here, or a combination of both. The first configuration has 2 photons in a right circular polarization state. The second has left polarized photons. Under parity, the momenta of the 2 photons change sign, but their spin, being pseudo-vectors, do not change. So the parity operation changes the first configuration into the second one, and vice versa. The photon wave function is characterized by its polarization vector epsilon, which points in the direction of the electric field, and for real photons is normal to the direction of motion. As parity is conserved in the decay process, this requires that the total wave function psi be an eigenstate of parity. Up to a normalization constant, the 2 possibilities correspond to the wave function psi1 and psi2 given here. The first is proportional to a scalar, so it has parity plus 1. The angle phi between the 2 polarization planes will be preferentially 0 with an intensity distribution proportional to the square of cosinus phi. The second is proportional to the product between a pseudo-vector and a vector, so it has parity minus 1. The angle phi between the polarization planes of the 2 photons will be preferentially 90 degrees. Experimentally, it is found that they are indeed orthogonal. The parity of the pi 0 is therefore minus 1. The charge conjugation operator, indicated by C, is an example of a transformation of the field itself and not of coordinates. It transforms the wave function of a particle, phi p, into the wave function of its antiparticle, phi p bar. The operation therefore changes the sign of electric charge, color, baryon, and lepton number. In short, all the quantum numbers of the charge type. Thus, the operator C applied to a fermion gives an antifermion, with all charges opposite, with the same mass, the same spin, and the same momentum. Again, electromagnetic and strong interaction conserves charge conjugation, that is to say that these interactions have the same intensity for particles and antiparticles. Weak interaction, on the contrary, violate C symmetry, so they distinguish between particles and antiparticles. Particles which do not have any charge can be eigenstates of C. They are their own antiparticles. The photon and the Z bosons are examples. The pseudoscalar meson pi 0, which is also its own antiparticles, has C phi pi equal to phi pi, with eigenvalue C equals to plus 1. Since the photon is generated by moving charges, we change the sign of their electric charge under C. C applied to a mu gives minus a mu. So charge conjugation is another multiplicative quantum number. A system of n photons will have C equal to minus 1 at the power n. For example, pi 0 decay into 2 photons respect the conservation of C, but pi 0 decay into 3 photons is forbidden. Indeed, the branching ratio of this decay is measured to be less than 3.1 times 10 to the minus 8. Time reversal operation, indicated by T, transforms the coordinate for vector x, so T, x, y, and z, into x prime minus T x, y, and z. When applied to field, T also turns them into their complex conjugate, and this is necessary because of the transformation of the equation of motion. Except for real boson fields, there are no eigenstates of T alone, so no conserved quantum number associated. The importance of T is rather in combination with the other discrete transformation, parity and charge conjugation. One can easily understand that all local field theories must be invariant under the joint action of CPT, transforming a process into itself. We will see in what follows that weak interaction violate to a maximum extent the symmetries C and P, and even the combined operation CP, which transforms a right-handed fermion into left-handed anti-fermion, is not respected by weak interactions. This introduces a small difference between a reaction and its reverse. It gives an objective direction to time. We will introduce weak interactions in the next video.